Hello, my name is Leibny Paola Garcia Perera. I am an assistant research scientist at Johns Hopkins University. Today, it is my very great pleasure to be presenting a talk on diarization. So let's go to it. The title of this presentation is The Yellow Brick Road of Diarization, Challenges and Other Neural Paths. First of all, I would like to thank all our collaborators. I really want to thank each one of them. You have made this work possible. From JHU, all the speech team, students and faculty. From Hitachi, Yusuke and his team. From CMU, Shinji. From NTT, Mark and Keisuke. From NTU, Susie and her team. And some other collaborators around the world. I have a disclaimer of this talk. I know that there are a lot of fascinating works that are not in this presentation. Apologies in advance. I chose the ones in which somehow I have been involved or have closely followed the research. So sorry. Technology is like a tornado. It abruptly changes our reality and takes us to different adventures. And in this case, Dorothy was the chosen one. And let's see where she got. We have arrived to the world of speech technologies with lots of devices from which we can gather data. But once we have all of it, how to make it useful is one of our goals. The first thing that comes to our mind might be that we need to categorize this data to find a way to label speakers or events or the things happening in those recordings. Labeling the recordings by speakers so that the output can serve other downstream tasks such as speech recognition or other related technologies is the main task. In this example, we have 3 speakers in a meeting having a conversation. So we should be able to label all of them. And for tagging these speakers, we need diarization. Diarization answers the question, who spoke when? Let's have an overview of what diarization does. So we have the speech signal, and the first thing to do is to get rid of the silences. For that, we use what is called a voice activity detection. After the voice activity detection, we can have a speaker type classification. We can decide whether it is a device or a real person. We can also search for the gender and classify between adult and kids. Afterwards, we can tag each of those speech segments and decide which ones belong to the same speaker. In our example, we have 3 speakers. Well, the overall process makes sense up to now. But how can we test the diarization systems? The most common metric is the diarization error rate, composed of summing up the false alarms, the misdetection, and the speaker confusion divided by the total time of speech in the recording. The false alarm is the duration of non-speech mistakenly classified as speech. The misdetection is the duration of speech incorrectly classified as non-speech, and the confusion is the duration of speakers classified as another speaker. Another metric is the Jacquard error rate. To compute the Jacquard error rate, for each reference speaker, we sum up the false alarm and the misses, divided by the union of the segments of the reference speaker and the hypothesis of that speaker. The final Jacquard error rate is the average of all the reference speakers' Jacquard error rates. Now that we know how to measure the diarization, let's take a look at some numbers. These are the diarization results for different subcorpora from the challenge. In the first graph, we have the results for the first DIHARD using an energy VAD. This was one of the first evaluations in which the corpora was heterogeneous, coming from different domains. As shown, the wildest domains got the worst results. Now let's constrain the problem and let's try to get the best results considering I have a perfect voice activity detection. Those are the results for DIHARD 2 best system and DIHARD 3 Hitachi and JHU solution. It is consistent for the three evaluations that the worst cases occur for the data like child-centered speech, VAST, which is YouTube videos, and restaurant scenarios. We know how to do diarization. We know the yellow brick road of diarization. This is the current pipeline that we follow. The boxes in blue are the ones that are optional, but in our brick road, it's mandatory to have the yellow ones. So we have an enhancement to denoise the speech signals. Then we have a voice activity detection to get rid of the non-speech parts. Then we have the embedding extraction to convert the speech into a mathematical representation that preserves the relevant information of the speakers. Then we have a scoring stage in which we establish similarity measures among those embeddings. Afterwards, we do the clustering where we group together segments that belong to the same speaker. As optional stages, we have the resegmentation, that is a refinement of the speaker boundary regions. And if we want to go fancy, we can apply an overlap assignment, that is to detect the regions where we have more than two speakers talking at the same time and assign labels to it. Finally, we can get the RTTM, which are the labels of the complete recording. Now, at super fast tornado speed, let me go through all of them. Enhancement. There are lots of denoising techniques. Today, I just want to point out two that gave improvement on previous diehards. The first one is WP, the weighted prediction error, to mitigate the reverberation. And the second one is the progressive multi-target network-based speech enhancement with signal-to-noise ratio preselection for robust speaker recognition. As shown in the figures, this approach is able to clean the signal from very high noise. Now, let's talk about the voice activity detection. We are considering that we don't have noisy condition. The recent most successful approaches include a neural network at some of their stages. For example, the neural network voice activity detection includes a SyncNet, a couple of LSTMs, and fully connected ledgers to give an output of speech and silence. On the other hand, we also have a hidden Markov model TDNN voice activity detection that consists of TDNN ledgers and bidirectional LSTMs. The posteriors obtained from this DNN combination are then post-processed using a hidden Markov model. Treating the frame posteriors like emission probabilities, we can apply a Viterbi algorithm and obtain the most likely label sequence. Let's talk about the embeddings. It is true that the better the embedding network, the better the performance. So we can see in the left graph that the extended TDNN got good results. But if we included augmentation, we can even improve those results. And also recently, the Microsoft team supports this claim by adopting a REST-to-NET as part of their main architecture for the Box Converse challenge. The scoring. Now that we have the embedding, we need a way to score them. The most popular method is probabilistic discriminant analysis. This method combines intersection variability and scoring all together. The idea of PLDA is to obtain a similarity matrix among all possible segments. Let's jump to the clustering. After the similarity matrix, we can group the same speakers using what is called agglomerative hierarchical clustering. And then at this point, we are ready to compute the RTTMs. But wait, agglomerative hierarchical clustering was good enough until the variational-based hidden Markov model clustering arrived. You can clearly see the difference in improvement. These are the results for the DIHARD 2 with agglomerative hierarchical clustering and the BBX. So BBX arrived to change the story. Mireya already explained the BBX clustering. But just to recap, the input to this system are the X vectors. And in the figure, each hidden Markov model represents a speaker, and the state transitions correspond to speaker terms. The state distributions or emission probabilities are single Gaussians. You can also notice that each speaker has a probability of P-loop, by which the hidden Markov model ends up back in the same state. With this approach, we can easily handle X vectors or any other embedding and produce speaker labels. We use the BB algorithm to infer the speaker distributions, the number of speakers, and the speaker sequence. For the resegmentation, we use the same idea as the BBX, but in the input, we have MFCCs at frame level. We can also observe the loop probabilities, and we have a GMM for the state distributions. We use, once again, the BB algorithm to infer speaker distribution, the number of speakers, and the speaker sequence. Now let's jump to the overlap assignment. Perhaps these architectures sound already familiar. They are exactly the same as the ones used for the voice activity detection approaches. But now they are trained in a certain way that the output is overlap, non-overlap regions. Both approaches are quite competitive. And finally, the overlap assignment. Once we have the posterior probability matrix from the BB resegmentation or the BBX, and by using the output of the overlap detector, we can assign the two most probable speakers to those overlapping regions. And well, the yellow brick road seems quite useful, but it has some issues. We are still trying to handle overlapping speaker. The system is not designed to minimize the diarization error, but optimizes every module independently. So as good engineers, we look for solutions. And the first that comes to our mind is, what about a fully neural path? That means a single DNN with a single optimization stage where the input is speech, or perhaps speech features, and the output are the labels, or perhaps speaker posteriors. But what about something in between? Because at first glance, the idea seems too risky. Let's try something first. This is our first trial towards end-to-end. The region proposal network-based speaker diarization was one of the first trials. It was inspired by the region proposal network used in image processing. The main idea is to find regions of objects and tag them accordingly. For example, in the picture, there are some labels for persons, dogs, known monuments, cars, etc. And the way to do it is to extract some feature maps from the picture using a set of convolutional layers. Then predict the object boundaries. After this, on the left side of the diagram, the region proposal network iteratively selects a bunch of proposal regions with redundant information. It serves as the attention of the network. On the right side, the network computes what is called a region of interest pooling. Both the information, the proposal, and the region of interest are then used by a classifier. The output is the picture with all the labels. Well, this sounds good, but is it possible to use it for diarization? The answer is yes. It is the same idea, but only in one dimension. So one neural network that outputs region proposals. Each of these region proposals contains speaker information that can be easily processed by different backends so that in the end, we can get an RTTM. Let's tackle the region proposal network for speaker diarization. The first stage is to compute the STFT of the signal and process it using a set of convolutional networks to obtain a feature map. The feature map is then sent to two branches. The first one is the region proposal branch. In the region proposal branch, the algorithm defines a sliding window and a set of anchors. Taking each anchor as the center, the system expands n times with predefined sizes. The anchors represent possible speaker segments with various sizes at different locations. These regions are inaccurate and redundant, so there is a regression layer that can adjust the timestamps, and a classifier which can distinguish between high quality and non-high quality segments. Those ones are referred as foreground and background segments. The output is a set of curated region proposals. The other branch goes directly to an algorithm called region of interest alignment. This is a pooling stage in which we ensure that the fixed dimension features in the feature map really reflect the STFT and mitigate the effect of quantization. The output of the region of interest is passed again to a regression layer, a foreground background classifier, and we include a speaker classifier from which we can compute the embeddings. The algorithm selects the speakers with highest scores. Then a non-maximum suppression model is included to get rid of proposals of redundant speakers. In a clustering stage, we use k-means, but it can be any other clustering algorithm capable of grouping the embeddings. Finally, we merge the regions of same speaker segments and obtain the final RTTM. The way to control this huge pipeline is with the following losses. The classification loss that decides if the speech segment is foreground or background. The regression loss is a smooth L1 loss to regress the central point and the length of the speech segments. The speaker classification loss that classifies the speaker identity of the speech segments. Some results on DIHARD show that we are getting closer to the best system. Now that we feel more comfortable, let's take a look at the end-to-end approaches. The idea of neural diarization is to design a neural network that can do the job in an end-to-end manner and can replace our previous modules. This is exactly what end-to-end neural diarization is trying to do. The way to do it is to define the diarization as a multi-label classification. This multi-label approach is a predictive modeling task that involves predicting 0 or 1 or 2 classes or the classes that I need. I mean, you can assign mutually non-exclusive class labels. This is exactly what EN or end-to-end neural diarization does, transforming the problem into a multi-level classification problem. It is a single network with supervision. In the following slides, I want to highlight very briefly the evolution of this interesting approach. The first one is like a proof of concept. It focuses only on 2 speakers. During the training, the system calculates frame posteriors from a neural network and computes the binary cross-entropy loss using the frame posteriors and 2 permutations of reference labels. To prevent label ambiguity, the algorithm minimizes the permutation-free loss. That means it chooses the minimum loss computed by the binary cross-entropy. At the inference stage, the neural network computes the frame posteriors. Then a threshold is applied to obtain each speaker's activity at every frame. Finally, we can compute the speaker labels. In a second approach, a set of bidirectional LSTMs are used to obtain the frame posteriors. It is known that the middle layers of a neural network can extract embeddings, so the algorithm includes a training criterion based on deep clustering loss. So it can group together the embeddings that are speaker dependent, meaning speaker 1 or speaker 2, or overlap or even non-speech. The final loss function encourages same speaker embeddings to remain together in the same cluster or separate them if they are in different clusters. This approach can work for multiple speakers. The next improvement of the EEN is to include self-attention. The bidirectional LSTMs depend on the past, future, hidden state, and the current feature. These bidirectional LSTMs are replaced by an attention layer that depends on all input frames. This encoder that is similar to transformer computes an all versus all frame similarity matrix. The encoder is similar to the transformer approach, but without positional encoding. As shown in the figure, the heads capture different characteristics. For this example, head 2 takes care of one speaker, and head 3 takes care of temporal dynamics. Now let's put all of them together. The first one for 2 speakers, the second one using the bidirectional LSTM with deep clustering loss, and the third one including the self-attention-based network. There is a problem with this EEN approach that it cannot handle variable number of speakers. The solution came with an encoder-decoder attractor. The starting point is a self-attention EEN from which we can compute the speaker embeddings. These embeddings are then fed into the encoder-decoder module. The LSTM encoder takes the embeddings and outputs the final hidden and cell states that go directly to the LSTM decoder. The decoder input are the sequence of zeros and the hidden and cell states from the encoder. The decoder produces a set of attractors that are controlled by a linear and sigmoid layer that calculates the attractor's existence probability. The system computes a series of attractors based on the embedding sequence. The dot product between the attractors and the embeddings plus a sigmoid layer produces the posterior probabilities of every speaker. And finally, the labels. Another method to solve how to deal with variable number of speakers is the speaker-wise change rule EEN. The main idea is that the activity of each speaker is estimated sequentially conditioned on the previous speaker's activity, following the change rule. It works as other sequence-to-sequence models, with a stopping condition. So for the full audio, we first obtain the posterior probabilities, let's say for Dory. And that is our first condition, to obtain the posterior probabilities for Lion, and then for the Tin Man, until there are no other speaker activities. The teacher forcing with a modification is used in this approach to prevent label ambiguity. And now we have here some results on the DIHARD 3 dataset on track 1 and the Oracle set. We can see the evolution of the EEN. Surprisingly, the EEN approaches are very competitive, and even in some cases, better than the traditional systems. We are almost at the end of the slides on EEN. Let's talk a little bit about online diarization. Up to now, only a few papers deal with the online diarization. To give a result at a desired time unit is not an easy task, but a modified EEN can deal with this scenario. So let's say that we have a 10-frame chunk and we apply EEN. It can be EEN EDA or the speaker-wise EEN. Then we get some posterior probabilities for 2 speakers. We take the ones with higher probabilities because they are supposed to be of cleaner regions, and we generate a buffer. This buffer matches the probabilities and also the frames. We want to increase the number of speakers, so we append some zeros to our posterior probabilities. The second chunk comes with another 10 frames. The first stage is to append the buffer and then apply EM. The solution again is a set of posterior probabilities for 4 speakers in this case. To prevent the label ambiguity problem among the chunks, we solve the permutation. Once again, we select the posterior probabilities buffer and match it with the frame buffer. We continue the process. As we can see in the figure, we have Dorothy as the first speaker, Tin Man as the second speaker, and Lion as the third speaker in the second chunk. And yes, more results on DIHARD 2. We have a comparison of the traditional systems and 3 options of online diarization. The proposed method is improving the offline baseline and is competitive to other methods. Another approach I want to mention is how to tackle the problem using our knowledge on source separation. In here, we have a neural network that takes care of everything. It is able to separate any number of speakers and mixtures in a recursive way. So we start with a residual mask or attention map and a spectrogram. The network pays attention to all the region and outputs a first mask. This mask corresponds to the first source. The residual mask is then injected to iteration 2, and it pays attention to the shaded areas. The same method computes a second mask corresponding to source 2. In the third iteration, the source 3 is obtained and the residual mask gets empty, finalizing the process. This procedure can be extended for different time steps, as it is the case for diarization, where we have multiple speakers talking at different times. Although the idea is the same, the method first splits the spectrum into consecutive blocks, and it includes a speaker embedding that is passed to the next block and guides the extraction of the mask of the same speaker. If the speaker does not appear at a given time step, the mask is 0, and the process continues until the residual mask is empty. The diarization error on simulated data is encouraging to continue exploring possible solutions in this direction. Now, are there ways to get the best of both worlds? Let's say part end-to-end and part embedding clustering? The answer is yes. Let's start with the EN vector clustering. This is an approach which was inspired by the EN and the clustering. Instead of just getting the posterior probabilities from the EN, we can get the embeddings. And with those embeddings, we can do clustering to prevent label ambiguity between different chunks. In the figure, let's say that we have 2 chunks and 2 speakers per chunk, although we have 3 participants. The encoder output is a modified EN, from which we can compute a diarization result. Let's choose Dorothy for the moment and obtain the posterior probabilities using a linear D1. Similar, we can compute the embeddings, linear S1, and perform a dot product between the embeddings and the posterior probabilities. We perform a time average and assign a cluster. A similar procedure happens for chunk 2, where the system chose Lion. We obtain a diarization result and the embeddings. The system performs the multiplication of the posterior probabilities and the embeddings and computes the time average. Now Lion goes to a second cluster. At the same time, the method does the same for the missing speakers. So now we get a point for a scarecrow and a new element for Dorothy. This happens iteratively until the process finalizes. The table shows an encouraging research direction using simulated data from liver speech. The proposed method with the chunking and the clustering gets better results for recordings of 5 minutes or longer when compared with the actual EN. Now let's talk about Doberlap. Inspired by Dober, we have Doberlap, a way to combine RTTMs that contain overlaps. The Doberlap has 2 stages, a label mapping that puts all the labels in the same space and the label voting that decides which regions get to the final RTTM. Let's say that we have 3 systems with 3 different hypotheses. We compute the tuple cost for all possible combinations. For example, this one, and then this one, and then this one, until we get a global cost tensor. Then we pick the lowest cost and assign the same label to it. And finally, we get the final mapping. For the label voting, we divide the RTTM into regions and estimate the number of speakers in each region. We assign the highest weighted N speakers in each region and compute the final labels. There is another interesting approach that uses EN as post-processing. I cannot tell you the complete story because this is a spoiler. Let's say that we have a nice system. For example, the output of the embedding clustering coming from the BBX or the embedding clustering with agglomerative hierarchical clustering, but it contains no overlap. The main goal of the EN is to estimate those overlaps in the current sequence. The procedure is as follows. We take the two longest sequence of speakers, in this case, Lion and Tin Man. We apply EM that give us the overlaps. We solve for any permutation issues using our previous knowledge of the speakers. Then we get the next pair, Tin Man and Dorothy, excluding the parts already used by Lion. We apply the EM and we solve for any permutation issues. Let's go for a third round. Our pair is Dorothy and Lion. We exclude the frames that were processed before and apply EM. We solve for any permutation issues and we assign the final labels. As I told you before, this is a spoiler, but here is a kind of recipe. We get the labels from another system, can be the BBX or an agglomerative hierarchical clustering system. Then we apply EM. Then we solve for any permutation issue. And finally, we get new labels with overlaps. Now, more results. This is the summary of the different systems. Systems that take the best of both worlds outperform their predecessors. For example, TDNN plus BBX plus EM as post-processing outperforms TDNN, BBX plus overlap. The overlap that fuses all the previous systems gets the best of each of them. And it considers overlap as well. It gets the best performance so far. These results are very nice, but wait, what about a difficult example? What is beyond what we have known so far? What is beyond diarization? In this slide, I'm showing you the results on two data sets that are focused on child-centered data. Well, the results are not very good. It can be because of the voice activity detection. It can be because of the annotations. It can be because of the overlap. But the truth is that the linguists and the cognitive science experts are waiting for all of us to really improve our error rates on these challenging scenarios. So we can see the best results with the Oracle VAD are around the 30s, and using VAD are around the 16s. So there is room for improvement. As an example, I can share with you 3 different recordings on this challenging scenario. And I remember that one expert told me, in real life, we don't have dev data. We only have eval data. So let's see. One that is not very crazy.
No, don't touch them. That is a calendar.
I want to time.
You want to look at the calendar?
Let's take a look at the second one, which is a little bit more challenging.
Baby,
Don't lick
that
it.
licking stuff.
That is
Stop.
You know what? I think other kids touch this, and if they got germs,
Then I say
it'll make
nasty,
you have some germies.
nasty.
he licked my
And finally, one that it is super challenging.
Wait, Susan?
You will see, you will see. Here you go.
So now we can understand why the diarization error rates fall dramatically. Finally, the takeaways. There are lots of flavors of systems to choose from nowadays. We have huge improvements, but we are not yet there. Neural diarization is becoming as good as embedding clustering methods. Overlap detection is still an ongoing research. Diarization to help downstream tasks like ASR is a must. They learn recordings, including child-centered data, cocktail party scenarios, need diarization solutions. Self-supervised learning for diarization can be a new research direction. Now let's see where the tornado brings us the next time. Thank you. Now we are ready for questions.